In production, raw LLM API calls that are placed inside standard while loops act as unmanaged and highly unpredictable execution liabilities. Without rigid boundaries, an autonomous model has no memory management, no predictable routing, and no mechanism to halt execution. Instead, it consumes tokens and executes blindly. OpenClaw serves as the structural antidote. It's a production-grade TypeScript AI gateway designed to field chat channel inputs through a controlled environment. The architecture decouples raw provider streaming from harness engineering. The model resides at the core, governed by a slate-colored harness layer. To see how this architecture functions, we will trace a single message: refactor the auth module, through the 5 stages of this harness layer. The engineering shell surrounding the model determines the reliability of its autonomous behavior. The turn begins when a chat payload enters the gateway's intake function, known as run agent harness attempt. Before any model tokens stream, the system evaluates the configuration, provider, and model parameters to resolve exactly which harness will govern the turn. Selection is deterministic. The request routes either to the built-in OpenClaw runner or to a registered plugin harness like Codex. This split allows the exact same GPT model to exhibit different tool surfaces and operational bounds simply by navigating a different harness path. If a plugin harness fails, the system surfaces the error rather than silently falling back to the built-in runner. This fail-close design ensures predictability. In production autonomy, a known failure is preferable to an unmanaged degradation of the safety model. Once the path is selected, the payload enters the lifecycle shell. This shell asserts the host system supports the context engine, initiating a diagnostic trace before model invocation. The core engine is the embedded runner. It operates a React-style loop where the model proposes actions and receives structured results in a continuous cycle. Execution relies on structured data blocks. The harness dispatches tool calls directly, which avoids the brittle string parsing required by traditional thought-action formats. Loop-boundedness depends on hard timeouts, policy denials, and a run-level abort controller. The architecture does not utilize a separate semantic loop detector. True system bounding requires a hard engineering abort. Probabilistic requests for the model to stop itself are entirely insufficient for production. When a gateway dispatches tools, it encounters the lethal trifecta. This risk emerges when a session combines private data access with untrusted inbound content and external communication capabilities. Traditional security models often rely on a read-only-hint in the tool schema, essentially asking the model to be careful. OpenClaw replaces hints with typed tool policies merged at harness selection. Safety is a structural execution gate. For shell commands, authorization depends on 3 parameters. The host target determines if code runs in a sandbox, gateway, or local node. Tiered security modes range from deny to full, while ask mode provides a human-in-the-loop gate explicitly pausing destructive commands for user approval. Since these mitigations are defined by configuration files, copy-pasting permissive setup snippets immediately compromises the security model. Guarding destructive system commands in production requires a typed hard execution barrier rather than a probabilistic model suggestion. Specialized workflows require the harness to inject procedural knowledge into the model's context via agent skills. Standard frameworks often struggle to manage more than a dozen tools without overwhelming the context window. OpenClaw manages catalog overload through progressive disclosure. The system injects lightweight metadata into the active context per turn, showing the model what tools are available without consuming significant space. Full procedural documents and model context protocol plugins only load on demand when the model explicitly calls them. This decoupling allows the agent's potential capability to scale while maintaining a minimal context footprint. The turn terminates when the model provides a final assistant message with no further tool calls. The lifecycle shell then classifies the outcome into one of 4 buckets: completed, aborted, blocked, or error. Context management is delegated to the specific harness that ran the attempt. The harness hook determines how the history is compacted. Final states are written across the system memory, including a shared SQLite database, per-agent storage, and session transcripts. Verification relies on the reasoning sandwich, using a strong permission shell inside the turn and external QA testing after the turn, rather than an internal LLM as a judge. Handling context management and verification outside of the raw generation layer results in an observable and debuggable system state. Effective harness engineering requires acknowledging inherent system gaps. OpenClaw lacks a first-class task graph. Multi-step planning is delegated entirely to the model inside the execution loop. There is no dedicated loop detector. Protection against spiraling execution relies strictly on timeout thresholds and manual aborts. Operators must also manage zombie memory risks. Stale facts persist in the SQLite tiers until a manual reset, as there is no automatic fact-TTL. These risks are managed by adhering to 3 core principles: deterministic harness selection, an enclosed React loop, and typed security policies. Ultimately, reliable production autonomy is a direct function of governed deterministic code, rather than endless probabilistic prompt refinement.